We are focused on finding eigenvalues today, and in the next video we will focus on finding eigenvectors. So let me remind you, lambda is an eigenvalue for some n by n matrix A, provided there is a non-zero vector v in Rn with AV as lambda v. And while lambda, the eigenvalue, is associated to this particular eigenvector, very nice. But as I mentioned, today we're focused on finding the eigenvalues. Okay, so let's unravel this, and this is kind of, or very similar to what we did at the end last time, just as a comment to an example. So this means, so thus, lambda is an eigenvalue for A if and only if A v minus lambda v equals 0 for some non-zero vector v. And this happens equivalently, I can say, or if and only if, equivalently A minus lambda I times v is 0. And so what we see from this is, well, I can say one more equivalently, I will say there is a non-zero vector v in the kernel of A minus lambda I. This is the n by n identity. Now, if you have a non-zero vector in the kernel of a matrix, that precisely means that the matrix is not invertible. Thus, lambda is an eigenvalue for A precisely when well, what do we know about matrices that are not invertible? Their determinant is 0. So precisely when the determinant of A minus lambda I is 0. And this is how we're going to find eigenvalues. Okay, so this is an equation in lambda, this, and it's called the characteristic equation. Of a matrix. And we practiced this sum, well, I mentioned this I think in the last video, we practiced this sum in the determinant section. But now we're going to write down this characteristic equation and then solve for lambda. And this gives us precisely the eigenvalues for a matrix A. Here's my first example, and it's really a question. And it is, when is 0 an eigenvalue for a matrix A? Certainly 0 can be an eigenvalue, but we know 0 cannot be an eigenvector. Well, let's consider this matrix A minus 0I is just A. And if you wanted to think about it this way, we would need the determinant of A, this, equals 0. And so the answer here, it's precisely when A is, so the answer, precisely when A is not invertible. 0 is an eigenvalue for A if and only if A is not invertible. And that's an important observation to make. Every time you have a matrix that's not invertible, 0 will be an eigenvalue. Let's find the eigenvalues of this matrix. It's a 2 by 2. And this one, I will also find eigenvectors, but it's the only one I will today because, as I mentioned, our focus today is finding eigenvalues. We have a whole nother video on finding eigenvectors, but I will illustrate it in this very first example just to give you a feeling of what's to come. Okay, well, what we need is we need the determinant a minus lambda I, and we need to set this equal to 0. So this is 1 minus lambda, 2, 5, 4 minus lambda. And we get 1 minus lambda, 4 minus lambda, minus 10. And we need to multiply all of this out and refactor. So we get lambda squared minus 4 lambda minus lambda plus 4 minus 10 lambda squared minus 5 lambda minus 6. And you notice this factors. I hope. I see 2. No, I don't. I see 6 and 1. So this will be, you have to pay attention to sign, lambda minus 6 and lambda plus 1. Okay, so we get determinant a minus lambda I is 0 if and only if, or provided when lambda is 6 or negative 1. So these are the eigenvalues. Now, for the purposes of this problem, for the purposes of today, we are finished. But as I mentioned, for this very first matrix, I will actually find eigenvectors. Maybe I can do them down here. And then the rest of the examples today, it's just going to be eigenvalues. Well, we know an eigenvector is a non-zero vector in the kernel of a minus lambda I. That's how we started today. So that's what I want to do for this. So for this eigenvalue, a minus lambda I is, well, 1 minus 6 is negative 5, and then I have 2, and then I have 5, and 4 minus 6, negative 2. So what is something in the kernel? Right, just check. We multiply this times this vector, we get 0. So this is, I was going to write down the equations. You know, this would say minus 5x1 plus 2x2 is 0. But then I could just quickly look at the matrix. It's just a 2 by 2 and find something in the kernel. So this is an eigenvector for lambda equals 6. A minus lambda I, we get 2, 2, 5, 5. And again, we can spot rather quickly here. For example, 1 minus 1 is an eigenvector for lambda equals minus 1. You can just take that vector and take this matrix times this vector and we get 0. Now, of course, these aren't the only choices I could have made, but for each eigenvalue, I found one eigenvector. And then, like I said, the rest of today, we're just finding eigenvalues. And we're going to come back to eigenvectors in the next video. Another 2 by 2. Let's write down determinant a minus lambda I, although we know one eigenvalue already because look, this matrix is not invertible. The second row is 2 times the first row, right? Not invertible. And so we know 0 is an eigenvalue. But let's calculate. We should see 0, and we should also find something else. Okay. So we have 1 minus lambda, 2, 2, 4 minus lambda. We get and then again, we multiply everything out. We have lambda squared. We have minus 4 minus 1. Then we have plus 4. And then we have minus 4. And you see we get lambda squared minus 5 lambda. Okay, so we do see that 0 is an eigenvalue, and we see the other one too. So determinant a minus lambda I is 0, provided lambda is 0 or 5. So we have two eigenvalues here. Now, let me make an observation right now. We have two eigenvalues. Notice. If I take lambda 1 plus lambda 2, and on the other hand, if I take lambda 1 times lambda 2. So on the one hand, I'm adding eigenvalues. On the one hand, I'm multiplying eigenvalues. This is 0 plus 5, which is 5. This is 0 times 5, which is 0. Now, these numbers are related to my matrix. Okay, maybe I got to do another color here. What's 5? Well, what else? Well, 5, I don't know. We could have all kinds of stories as to what 5 is, but the point I'm trying to make, look. 5 is, for this matrix, this is also a 1, 1 plus a 2, 2. And what's 0? Well, for this matrix, or I could have written it AD minus BC. Maybe I should do, oh, it's fine. I'll leave it like this. And each of these is something. This is what's called the trace. It's denoted like this. And this is where you just add the diagonal entries. And this one is the determinant. That's why I almost changed it to write it like AD minus BC. Okay, and this is not just this example. You can say more generally, anytime you have n eigenvalues, if you add them up, you get the trace of the matrix. If you multiply them, you get the determinant of the matrix. Now, sometimes we saw an example last time of a matrix that had no eigenvalues. And so you couldn't make this statement. But if you have an n by n matrix and you have n eigenvalues, sort of, I'll say more about this soon. You could add them up, get the trace, multiply them all, get the determinant. But then there's more here. Another thing that I'll say to sort of connect the trace and the determinant to this example, and generally, I think I will erase this part. It's fine because we can, everything I need is still on the board. What we notice here, so this is an observation. Well, we see already, in this example at least, that this is a polynomial, and it always will be. And of course, you set this equal to 0, now that's an equation, and it's called the characteristic equation. But just this, which is just this, not set equal to 0, this is called the characteristic polynomial of a matrix. Okay, And it will be, if A is n by n, it will be a degree n polynomial. We're going to see more than just degree 2 today. I'll do some degree, or a 3 by 3, 4 by 4, a couple like this. And then if A is 2 by 2, this characteristic polynomial, oh, sometimes it's denoted like this, f a of lambda, because it's a polynomial in lambda, right? We see it here. So if A is 2 by 2, the polynomial looks exactly like the following. We have lambda squared minus, well, the trace times lambda, and then plus the determinant of A. Okay? We see that in this example, right? We have the trace is 5, the determinant is 0, and my characteristic polynomial is lambda squared minus 5 lambda plus 0. This is the way it works for a 2 by 2. Now, personally, me, I wouldn't spend the time to necessarily memorize this because it's not that hard to just take A minus lambda I for a 2 by 2 and then take the determinant of that. Let's prove this for 2 by 2. Here we go. Well, A minus lambda, determinant A minus lambda I is this. A minus lambda B C D minus lambda, which is A minus lambda D minus lambda minus BC. And now, just like we did in the two by 2 examples we've already done, let's multiply everything out, although in this case I will not be refactoring. So we get lambda squared, we have minus d lambda minus a lambda plus ad minus bc. And now you see we've basically proved it. Let me just rewrite it one more way. Minus a plus d lambda, and then plus, I'll put a parenthesis here, maybe I'll use this notation here. This, we have 1 minus lambda, 3, 4, 3 minus lambda, 2, then zeros, 0, and minus 1 minus lambda. Now you have choices. One thing I like about this section is it's a nice review of determinants, and we have choices. So I'm just going to expand about the first column because I have 2 zeros, or I could have similarly done the bottom row just to make my life easier. And so I see this is 1 minus lambda, and then we have times, we cross off this column, cross off this row, we have this determinant. And then now we just have this product. So this is 1 minus lambda, 3 minus lambda, and minus 1 minus lambda. Now, okay, we see it's the product of the diagonal entries, and we could have just started that way. Remember, when we're taking the determinant of an upper triangular or a lower triangular matrix, the determinant is the product of the diagonal entries. Although it didn't take that long to take this intermediate step. Okay, so we see the determinant of a minus lambda I, or this characteristic polynomial, is 0 when lambda is 1, 3 minus 1. And this is general for an upper triangular or lower triangular matrix. So this is general, I'll put stars, if A is upper triangular or lower triangular, the eigenvalues of A are the diagonal entries. And this comment that I made about if you have n eigenvalues, so they will be the diagonal entries, say A11 all the way out to lambda n is A and n. This comment about adding them up, without a doubt, this is the trace because these are the, oh, maybe I'll just put TR. These are the diagonal entries, and similarly, if you multiply them, we get the determinant. We know this is also the determinant of upper triangular or lower triangular matrix comes from just multiplying the diagonals. So this was a comment that I made for 2 by 2, but as long as you have n eigenvalues, then it holds 2. So I proved for 2 by 2 the characteristic polynomial has this form that has the trace appearing here and the determinant appearing here, and is that generally the characteristic polynomial has this form. Well, we see it's a degree n polynomial, and we see the trace, and we see the determinant, and then we have a bunch of other terms that we don't have like a way to describe them so nicely, like the trace and the determinant. But it's an important observation to realize that the eigenvalues of A, which are the solutions to setting this polynomial equal to 0, these are precisely the roots of a characteristic polynomial. This lets us see, for instance, that, well, you know any polynomial has no more than n roots, and so we get immediately from this sort of observation that for an n by n matrix A has no more than n eigenvalues. Well, we just saw a 3 by 3 that had 3 eigenvalues, but last time we saw a 2 by 2 that had 0 eigenvalues. And you can have, well, we could have a 3 by 3, and maybe we will today, that has only 1 eigenvalue, for example. But this leads to the following definition. Before we get into more examples, the algebraic multiplicity of an eigenvalue lambda 0 is k. I'm defining this algebraic multiplicity provided the determinant of A minus lambda I, or I could have written it like this, right? But this is lambda minus this particular lambda 0 to the k times g of lambda, where g of lambda 0 is not equal to 0, okay? This is just, you know this from polynomials, right? You can have a polynomial that has a repeated root, for example, and this counts the multiplicity of that root. And then one more thing I will say is the notation here. Mu stands for algebraic multiplicity of this particular eigenvalue is k. So that's what we write Okay, now back to examples. Here's another 3 by 3 matrix. This one we cannot just, well, it's not upper triangular, it's not lower triangular. We can't just look and pull off the diagonal entries as our eigenvalues because, well, it won't turn out that way. So we need to compute this, or same thing as this, right? A minus lambda I. We take 7 minus lambda 0, 3, minus 3, 2 minus lambda, minus 3, 0, 1 minus lambda. Well, you have some choices. We can expand determinants about any row or any column. And if you look here, this column would be the one where I have the least number of steps because I have 2 zeros. Okay, so that's what I'm going to choose. So this is, but I have to pay attention. This is plus, minus, plus. So I will have 2 minus lambda. And then I cross off this column, cross off this row. I get 7 minus lambda, 3, minus 3, and 1 minus lambda. So I have 2 minus lambda times and then plus 9. Now let me give you a little piece of guidance. It's not a very good idea to multiply everything out because, well, sometimes it's hard to factor a cubic polynomial. So here, I already have this, so I'm going to leave this alone because, without a doubt, if I evaluate what I have so far at 2, I get 0. You can even see that here. And so I will have 2 is a root of this polynomial, or equivalently 2 is an eigenvalue of A. So all I'm going to do is leave this. Then I will work with this part. I will multiply this out. Then I just have to refactor a quadratic, or worst case, I have to use quadratic formula. Okay, that's something much easier than working with a general cubic. So I leave this alone. And then inside I get lambda squared minus 7 oops, it's supposed to be a 7. 7 lambda minus lambda. Then I have plus 7 plus 9. I get 2 minus lambda. Okay, lambda squared minus 8 lambda plus 16. Okay, very nice. Then I get, now I can factor again. I have 2 minus lambda, and then this will be either lambda minus 4 or 4 minus lambda. I'll write it this way, squared. Okay, our eigenvalues, well, we have one that's repeated. We have one that has algebraic multiplicity 2, and it's lambda equals 4. So here, if we finish this, we see that this A minus lambda I is 0 when lambda equals, we get 2, 4, 4. And lots of times here, this is how people will list them. If something's repeated, you just list it multiple times. Or you could also use this notation that we just discussed, this algebraic multiplicity of 2 is 1, and the algebraic multiplicity of 4 is 2. That's using this other notation here. Let's see. Also, what's true is, remember I said that a matrix has no more than n eigenvalues, but it's also true that you have no more than n eigenvalues if you count them with multiplicity. So here, if you count multiplicity, I have 3. I have 2, 4, 4. Of course, I only have 2 distinct eigenvalues. But if you count them with multiplicity, it's 3, like this. Okay, let's do another example. Characteristic polynomial, it's this determinant where we have 2 minus lambda, 1, 0, minus 1, 4 minus lambda, 0, 5, 3, 3 minus lambda. And much like the last example, you see I have zeros. This column would be my best choice to expand upon because I have 2 zeros in it. It makes my life shorter, easier. Okay, so I get, this is plus, minus, plus, minus, plus. I get 3 minus lambda times this determinant, where I cross off this column, cross off, oh, pardon me, cross off the bottom row, like this. Is that 2 by 2? 2 minus lambda, 1, minus 1, and 4 minus lambda. And then we get 3 minus lambda. And again, look, this is our degree 3 polynomial. We already see that if we evaluate this as it's written at 3, we get 0. So you don't want to multiply this term in with all of this. You will just have to refactor something that's degree 3, which can be challenging. So I'm going to multiply all this out, and then I just have a quadratic to factor. Okay, so I leave this part, and then I get lambda squared, minus 4 lambda, minus 2 lambda, plus 6, plus 8, plus 1. I said they wasn't looking right. 4 times 2 is 8. Okay, very good. And we get, I'll write it below. You see what we get? This is going to be interesting. Lambda squared minus 6 lambda plus 9. And this factors, this is exactly lambda minus 3, or 3 minus lambda squared. So we get 3 minus lambda cubed. So you notice we only have one distinct eigenvalue, but it has algebraic multiplicity 3. So determinant, maybe I'll write it this way, f a lambda equals 0, provided we could write it this way. So the algebraic multiplicity of this here. And maybe I will just write in a box what I verbally said, because we saw it in the last 2 examples. In the last 2 examples, we did not have 3 distinct eigenvalues. We had 2 distinct. This one we only have 1 distinct. But I mentioned this, and it's worth writing, an n by n matrix, and this is not a good place to stand for you to see what I'm writing. An n by n matrix has at most n eigenvalues, even if you count them with algebraic multiplicity. And that's just because of what we know, how roots of polynomials work. If you have a degree n polynomial and you have a bunch of repeated roots, say, you add up the multiplicities of the roots, you get no more than n. Okay, now let's do a 4 by 4 example, and let's compute the eigenvalues. Well, this characteristic polynomial, which is this determinant, I'm going to need a lot of space for a 4 by 4. We have 8 minus lambda, 1, 3, 6. We have 0, 2 minus lambda, 1 minus 1, 0, 0, minus lambda, minus 4, and 0, 0, 1, minus lambda. Oh, but again, look. This column is going to be the one I want to use first because I have this only one non-zero entry. We always want to make these calculations as simple on ourselves as possible. So this will be equal to 8 minus lambda times this 3 by 3 determinant, then plus 0. So we have 2 minus lambda, 1 minus 1, then we have 0, 0, minus lambda, 4, 1 minus lambda, minus 4, like this. But now this 3 by 3 determinant, well, I can expand about again the first column, and I'm only going to have one term in the sum for this determinant. So now this equals 8 minus lambda, 2 minus lambda, times this 2 by 2, minus lambda, minus 4, 1 minus lambda. And finally, we get 8 minus lambda, 2 minus lambda, and then we get lambda squared plus 4. Okay, great. What do we see here? Okay, fine. Lambda's 8. Okay, fine. Lambda's 2. Here, problematic. There are no real solutions to lambda squared plus 4 equals 0. So we see here the determinant of A minus lambda I is 0 provided lambda is 8 or 2. These are the only real solutions, and the algebraic multiplicity of 8 is 1. Algebraic multiplicity of 2 is 1. So it's not the case that you always have n, 4 in this case, eigenvalues. Even if you do count algebraic multiplicity, you can have less than that. I could have made a 4 by 4 example where we had no real eigenvalues, just like we saw in a 2 by 2 example last time. Okay, so here we have only 2, even counting their algebraic multiplicity in this 4 by 4. Well, what is true is, let's say A is n by n with n odd, then A has at least one eigenvalue. This really comes from the fact that if you have an odd degree polynomial, it has at least one real root. Okay, even is definitely not true. You could make a 10 by 10 matrix, for example, with no real eigenvalues. But if you had 11 by 11 or a 9 by 9, then you have at least one eigenvalue, real eigenvalue, of course. Okay, so let's move into a little bit different types of examples. Let's consider the following matrix: A, 1, 1, K1. And the question is, for what K does A have, and then there'll be two parts. Part 1, for what values of K does A have two distinct eigenvalues? And then the second part is no eigenvalues. Okay. Well, the first thing that we need is, we need this determinant, a minus lambda I. Although, you know, we talked about what this is in terms of the trace and things like this, so maybe I'll just write it like this. The characteristic polynomial, it looks like this. It's lambda squared minus the trace plus the determinant. Lambda squared, the trace here is 2. Uh-oh, I forgot my lambda. And then the determinant is 1 minus k. Okay. Well, I mean, honestly, I just did that. I just wrote it this way because we talked about that. But I personally wouldn't memorize this because you notice I even left off a lambda. I would just have done a minus lambda I, taken the determinant. Either way is perfectly fine, and we will get this characteristic polynomial for this matrix. But now we have to answer the question. We have to think about, what does it mean to have two distinct eigenvalues, and what does it mean to have no eigenvalues? Well, this comes down to quadratic formula, right? Sometimes you can factor, and that's great, but not always. Quadratic formula, when you have a quadratic, will always give you the roots, or you'll be able to see that you don't have any real roots. So what I need to do is consider the following. Well, what is quadratic formula? Negative b plus or minus the square root b squared minus 4ac all over 2a. And we know precisely when this has two solutions and when it has no solutions. There are two solutions to this. So b squared minus 4ac positive gives us two solutions. B squared minus 4ac negative gives us no solutions. And it wasn't really asked here, but if we had b squared minus 4ac equals 0, we have exactly one solution. So let us just translate that into this problem. Maybe I'm going to come over here and make a box. Okay. So all I have to do is look at this. B squared minus 4ac equals, it's 4 minus 4, 1 minus k, which is 4 minus 4 plus 4k, which is, one more step, 4k. Okay, this is this b squared minus 4ac. And so we see the answer when 4k is positive, two solutions, 4k is negative, no solutions, but we can state that entirely in terms of k. So we see, I'll do it here, when k is positive, we get two distinct eigenvalues. And then, let's see, I'm going to have to continue my box. When k is negative, we get no eigenvalues. Okay. Well, here's another example, kind of in the same spirit as the last, where we have a matrix that has k as one of the entries. But the question is, for what values of k does this matrix have lambda equals 5 as an eigenvalue? Well, you see, what I really need is the determinant of a minus 5i. I need this to be 0. So I can just go ahead and do this. maybe before I start calculating determinants, I will just add these entries along the diagonal. This becomes minus 6k, 2, 4, minus 2, 7, and then 0, 0, negative 3. Okay, so you see, this is one thing I like about this section is we have a very nice review of the cofactor expansion, where we get to choose our favorite row or column to expand. But you see, looking at this row has 2 zeros. So I would choose this to expand. Makes your life a little bit easier. Okay, so this is equal to, well, it's plus, minus, plus, minus, plus. It's going to be negative 3 times. We cross off this column in the bottom row. We get minus 6k, 4 minus 2. And then this is minus 3 times, we get 12 minus 4k. We want this to be equal to 0, okay? So determinant a minus, 5i, pardon me, equals 0. Well, minus 3 is never 0, so it says this part must be 0. 12 minus 4k is 0, or we see that k would need to be 3. Okay, so this is our answer to this problem. Last time when we talked or started to talk about diagonalization, I introduced this notion of a similar matrix. And I said that A was diagonalizable provided it's similar to a diagonal matrix, and similar was this definition, that there exists some invertible n by n matrix S such that A is S inverse BS, okay? But the word similar for two n by n matrices, they don't need to be diagonal, or one of them doesn't have to be. You can have any, you can say A is similar to B, or they're just two n by n matrices, provided there is this invertible matrix S with A is S inverse BS, okay? Now, what I'd like to do is think about this idea of similarity with matrices and their characteristic polynomials, or equivalently, what does that say about the eigenvalues? And this is what I want to discuss now. So what I'd like to show is if you have two similar n by n matrices, that their characteristic polynomials are the same. And how can I show this? Well, first, let's just think about this. If I take, let's say, A minus lambda I, and I have this, right? This is S inverse BS minus lambda I, but this is the identity, and this is a constant scalar, right? So I can write this as follows. I can write this as S inverse BS minus, I'll put the S inverse lambda I S, because let's think about it for a moment. Certainly the identity is S inverse times S, okay? But then we know when you take scalar times a matrix, you can either multiply it on this side, multiply it on this side, or if you have a product of two, put it in the middle. It doesn't really matter. It's just a scalar, okay? That was one of our properties of matrix multiplication. So without a doubt, lambda I is equal to this, okay? Because I could, like I said, pull out the lambda here and then multiply those two matrices and you just get the identity. But now, one more property of matrix operations, I should say, and then I will get to take determinants. This is, well, I can pull out an S inverse here. It would be S inverse, and then I would have BS minus lambda I S. And similarly, I can pull out an S on this side. So this is S inverse B minus lambda I S. What we see is if A and B are similar and related by this equation, A minus lambda I equals S inverse B minus lambda I times S. Now, let us get back to the characteristic polynomial. So, f A of lambda is the determinant of A minus lambda I. This is the determinant of this big thing, S inverse B minus lambda I S. But what do we know about determinants? If you have determinant of a product, it breaks into determinant times determinant. And, well, it's the same thing for 3. So this is determinant S inverse, determinant, put parentheses, pardon me, determinant B minus lambda I, and then determinant S. But one more property about inverses, the determinant of S inverse is 1 over the determinant of S. So we just get this, which is this, f B of lambda. Okay, so I have in fact shown if you have two similar matrices, means they're related by this, was for some invertible matrix S, they have the exact same characteristic polynomial. And so what this means, maybe I'll erase this part, we get from this, maybe I'll do this in black. Well, they not only have the same characteristic polynomial, but similar matrices have the same eigenvalues with the same algebraic multiplicities, because you just take the roots. Well, you have the same polynomial, and you're just looking at the roots. What else do we get from this? Maybe I will erase this other part too, the rest of the proof. We also get similar matrices, have the same trace. And determinant, just because as I mentioned, the trace and the determinant are certain coefficients that appear in the characteristic polynomial. So if their characteristic polynomials are equal, then their traces are the same and their determinant is the same. You could also see the determinant is the same just by working directly with this equation, but I mentioned it as a consequence of having the same characteristic polynomial. So this is one really nice thing about similar matrices, the same eigenvalues. So consider an n by n matrix A, okay? Then if you take A minus lambda I transpose, well, if you think about this here, the lambda I part is along the diagonal, and when you transpose, you interchange rows and columns, the diagonal entries, they stay diagonal entries. So this will be A transpose minus lambda I. Okay, so now let's think about this, the characteristic polynomial of A, which is the determinant of A minus lambda I. Well, we know if you take a matrix, here's a matrix, A minus lambda I, it has the same determinant as when you take the transpose. So this determinant is the same as the determinant of A minus lambda I transpose. This is a property of determinants. But then this and this are the same as matrices. And finally, this is the characteristic polynomial for A transpose. So just like when I was making my observation about similar matrices, this is a, I was going to say a similar observation. This is a, what else do I say besides similar? This is a corresponding property, or very much like property, to not reuse the word similar, for the transpose. So we see the characteristic polynomials of A and A transpose are the same. And we also get from this that A and A transpose have the same eigenvalues with the same multiplicities. So this is a nice observation to close with. And then, well, we already knew that the determinants were the same, so I won't make that comment. And then the traces are the same because the diagonal entries don't change when you take transpose, so I won't make that comment here either. But this is a nice observation that we get just by looking at characteristic polynomials. And then, as I mentioned, the next video is when we will practice finding the eigenvectors corresponding to eigenvalues.